All right, let's look at some examples for Module 5, looking at inductors and capacitors, kind of taking a step back and looking at some problems, not just AC sinusoidal, but going back to some of the basics where we're going to need to do some, maybe a little more calculus kind of answers here. But first off, let's just do some combinations. So this is stuff we did in physics, but for number one, we're going to take the circuit and combine it into an equivalent inductance, just one inductor between the two terminals. So looking at this circuit, we need to think about parallel and series combinations, and we need to watch out for tricks, right? So this one is a kind of a tricky circuit because notice this connection here is shorting out these two. So if we had current flowing this way and it comes and decides it's going this path or is it going to go in this path, all the current will go through this path, right? None of it will go through those inductors because they are just like resistors. They have resistance to the flow, so they will be unfavored. It'll always take the short circuit path. So these two are gone. They're not even part of the circuit really because they're shorted out. The wire is directly connected from, these are in series with each other, and end to end the short is shorting them out. Similar story for this 40 millihenry inductor because again there's a direct path from one end of the inductor to the other. Right, so again, current coming this way will all choose to go around that inductor. None of it will go through, so that inductor is basically not in the circuit. So for this circuit, kind of a trick circuit, but for part A, L equivalent is what? Well, so we have 10 millihenries in series with 50 millihenries. Hopefully you can see that, right? And this comes right in here. This is like one node. And so how do we combine inductors in series? Remember, inductors for series, L equivalent is just L1 plus L2, just like inductor, or just like resistors. For parallel, just like inductors, L equivalent, yes, series parallel is 1 over L1 plus 1 over L2, so forth, okay? So in this case, all we need to do is 10 millihenries plus 50 millihenries, because they're in series, and so L equivalent is just 60 millihenries for A. All right, for part B, we got capacitors. All right, so same story here, and the circuit looks quite a bit the same, except for now instead of a short circuit there, we've got a capacitor in there. So what does that do to this problem? Well, changes everything, right? So now we don't have anything shorted out because now these two capacitors in series end up being in parallel with this 5, which is also in parallel with this 5, right? So, and then that whole group will be, if we make it into one capacitor, one equivalent of that bunch, will be in series with these other two capacitors here. So we can do it step by step, or we can just kind of write it out. But how do we do capacitors? How do they combine? So in series, remember capacitors are the opposite of inductors and resistors. So in series, C equivalent is 1 over C1 plus 1 over C2 plus however many are in parallel, right? And are in series. And then in parallel, C equivalent, series, parallel, they just add C1 plus C2 plus however many are in parallel, all right? And so let's think about this here. Let me see if I have a different color. So hopefully we see these two are in series, right? So if we combine those two in series, then we have 3 capacitors in parallel, right? Because hopefully you see these two, those ends are connected and these ends are connected, so these two are in parallel. And then if this is one capacitor, that capacitor will be also end-to-end connected, and so it'll be in parallel with that. So so let's call this C equivalent 1. So C equivalent 1 is 10 in series with 10, which is 1 over 10 plus 1 over 10. All right, capacitors in series look like resistors in parallel. And if you've done this enough times, when you have two things like that that are the same size, it's just going to end up being 5 microfarads. But if you don't believe me, plug it in your calculator and prove it to yourself. But so C equivalent 1 is also 5. So now we've got 3 5 microfarad capacitors in parallel, right? And so if we're gonna, kind of cheating here, but take all those and combine them into one. I guess let's just go ahead and redraw it. So we're gonna have some, whoops. So these are my C and D terminal points, but we have, and then the 7 microfarads is still here and the 8 microfarads is still here, but we'll call this C equivalent 2, and C equivalent 2 is 5 microfarads in parallel with another 5 microfarads in parallel with another 5 microfarads. Right, 5 plus 5, and then the 2 10s made another 5, so we have 3 5s. Capacitors in parallel just add up, so C equivalent 2 is just 15, so just 5 plus 5 plus 5, so it's 15 microfarads is C equivalent 2, right? So now we want C equivalent total, just a C equivalent equals what? Well, it's these 3 in series, right? So C equivalent is going to be 1 over 15 plus 1 over 7 plus 1 over 8. And these are all microfarads. We see that? No? There we go. Microfarads, microfarads. But since everything is microfarads, we can just put them in as whole numbers, and then the answer, just remember that the answer will come out as microfarads. So we can do 1 divided by parentheses 1 divided by 15 plus 1 divided by 7 plus 1 divided by 8, and just make sure you got your, anyway, know what your calculator is doing, knowing whether the parentheses are working right. But so mine gives a nice picture of it, so I can see that yes, it did do the 1 overs all right, and I would rather have a number. So we get 2.99 microfarads is C equivalent. All right, so the total C for all those put together, if we wanted to have it just be one capacitor, it would be a 2.99 microfarad capacitor. Okay, so just a little reminder, parallel series stuff, how we do it with capacitors. Remember, if we had changed these to AC into impedances, they would just combine as resistors, and we could combine like resistors do, and we could combine inductors to capacitors to resistors. But we're kind of taking a step back and separating out. But now let's look at an example. What do we do if we have some, well, I'll call this number 2, I guess. If we have a circuit that has, let's put a switch in here that can come closed at some time. What if we have a circuit that has a resistor and a capacitor in it? All right, and at some time t equals 0, we're going to close the switch, and we're going to assume that the capacitor, well, we have a capacitor voltage, and we'll say that V sub C at 0 is not 0. Let's say, so we have a charged capacitor, we're going to close in the switch, and then the capacitor will discharge through the resistor, because capacitors store energy, capacitors and inductors store energy, so we can have it, if it's not closed, no current flowing, the capacitor will store charge, hold energy, but then when we close it in, the resistor, they're a lossy element, we can use them to represent losses, but they dissipate the energy, so it'll use up all the energy, and then the circuit's energy will go to 0. So when we close the switch, current will start to flow. Eventually, the current will die out because the energy dies out. And you can't see that. Here we go. Let me get myself going here. So we've got a capacitor with a switch and a resistor. So let's just, should we put in some numbers? I don't know. Let's just say, let's just put in 10 volts for now. So V sub C at 0, at time t equals 0, so this is V sub C as a function of time, it would be a small lowercase or cursive kind of thing, is some number, right? Some value that's not 0. And so let's say we want to get an equation for what's going on in here. So we go back to the calculus or to the definitions. And so for a resistor, we had Ohm's law, right? V equals I times R, or I equals V over R. If we have some, well, the voltage is the same across both of them. But in general, this is the equation. For a capacitor, remember the defining equation for a capacitor is I is C dV dt. All right, the current through a capacitor is proportional to the derivative of the voltage times capacitance. And so if we want to do, let's say, KCL at the top node, call it 1, I guess, call this ground, doesn't really matter. KCL node 1, what are we going to have? So I guess we can, let's just take it as pieces here. So, how do I do this? The capacitor is going to be acting as a source, but just for positive sign convention, let's just go ahead and name lots of things here, even though a lot of them are the same thing. So the current, we'll sum the currents out. So we'll call this I sub C and this I sub R, I guess, V sub R, with everything named. And so doing KCL at node 1, we would say out equals in, I sub C plus I sub R equals 0, because there's nothing coming in, right? So I sub C is equal to negative I sub R. And then we can put some C's and some R's. Keep track of things here. Okay. And so I sub C is C dV dt, so we got C dV sub C dt plus 1 over R V sub R equals 0. But now we look, and these are out, they're in series, but they're also in parallel because there are only 2, right? And because the bottom, if this is a ground node, both of their negatives are there, and the positives are on the same node as well. So V sub C equals V sub R. So we could just write a differential equation, C dV dt plus 1 over R times V equals 0. Right? And so where we're just saying V equals V sub R equals V sub C is the only voltage in the circuit, basically. All right. And so we want to see what's going on here. And so we want to, this is a differential equation. We want to solve the differential equation. How do we solve differential equations? If you haven't had diffie-q, maybe you're going, I don't know. But we're just going to, I don't know if it's called really cheating, but we're going to know that we have a differential equation, constant coefficient, linear differential equation. And so we know the solution is of the form V of t is some, what do we want to call it? Some k e to the st kind of form. So it's an exponential kind of form, has t as a variable, right? That's the derivative, t is our derivative variable. Some constant k, some constant s, or some values k and s that we don't know, that we need to determine. And so one way of solving this is to just put that into the equation, put these values into the equation, and solve. And so we want to, let's just plug it in how we are. We might have a bit of algebra to do, but so let's plug in this V kind of template form, this form of the voltage, and see if we can use the equation and our initial conditions and so forth. We may put in some numbers to get a solution for V as a function of time. And then we could get I as a function of time, the current as a function of time also once we have the voltage. And so we'll say C times dV dt. Well, what's the derivative of this? Is derivative exponential, you just multiply by the exponent, and it's just the exponential back. So it's going to be ks e to the st is dV dt, right? Plus 1 over r times v, which is just k e to the st equals 0. Alrighty, and so is this going to get us anywhere? What can we do with this? Well, the e to the st's cancel out. K's cancel out. And so what do we have? We have CS plus 1 over R equals 0. If I'm not losing anything here. And so S equals 1 over RC, negative 1 over RC. Looks good. Okay, so we've got one of our unknown parameters in our voltage equation, but we still don't have K. K just went away, right? So what can we do to figure out K? And let's go ahead and use our, what else do we have? We can use our initial condition. So let's say we know that V sub C is also what we call V, right, from here. And so V at 0 is 10 is equal to, just plug in 0 for here, so K e to the S times 0, right? Plugging in, this is T, so plugging in T equals 0 here. And so e to the 0, anything to 0 is just 1, right? So that's equal to K, so K is 10, right? Or in general, K is equal to V naught, whatever the beginning voltage was. Okay, so we got it, right? So V of T then is 10 e to the negative 1 over RC times T, volts. All right, and so what does that look like? It's an X, so if we want to put V of T versus time, when T is equal to 0, that's 10, we already established that, and then it's a decaying exponential, right? It's got a negative coefficient, R and C are positive numbers, and so it's just going to be an exponentially decaying kind of thing, right? So V of T would look something like that. So that's kind of what we expect. We have a charged up capacitor, we close in the switch, the resistor loses all of our energy for us, and the voltage goes down to 0. How about the current? What does the current do? Well, we could either use I is C dV dt, or we could use I is V over R. Well, I like I is V over R. So I, going this way, clockwise, I sub R, function of time, is 1 over R times V of T. And so, anyway, we didn't put in a number for R, but basically it's another decaying exponential, right? 10 over R e to the negative 1 over RC times time. Okay, so the current is also going to have a different peak value, 10 over R, whatever that is. And it's also going to be a decaying with time kind of exponential. Okay, let's look at an inductor problem now that's got this time dependence in it. So let's just kind of do a little bit here. Let's say we have 2 inductors in series. Bad writing here, but 20 millihenries, 50 millihenries. I'm going to say this one's 70 millihenries. And we know we got some sort of a closed loop, some sort of a source over here, and we know the current through it is I of the inductors is 10 e to the negative 50t amps. Kind of getting messy here, but hopefully you can see that. And so let's just say we want to know the voltage across this whole thing, V sub L. Let's call it V sub L. Okay, so let's go ahead and combine these inductors into one. So we have a nice current through one thing and the voltage across the same thing kind of situation. So we'll have L equivalent. So what do we have here? We have 2 in series, and that's in parallel with the third. So we say L equivalent. Remember, inductors combine like resistors, so it's just going to be 20 millihenries plus 50 millihenries. That's the 2 in series, right? And then that combination is in parallel with 70 millihenries, right? So this is going to be 70 in parallel with 70. So it's going to be 1 over 70 plus 1 over 70, which again, 2 things in parallel that are the same, cuts it in half. We've got 2 1 over 70s, and so that's going to be 70 over 2, which is 35. So L equivalent is 35 millihenries. And now let's go back to, okay, what is the defining equation excuse me, for inductors. So for capacitors, we had I is C dV dt. Inductors are just the opposite, or the dual. We switched the C and the V, and we changed it to, the V and the I, and we changed it to an L. So we're going to say V of the inductor is L di dt, just to remember. This isn't proving anything, it's just recalling equation from physics, basically. So V is L di dt. Going back to Faraday's law and all kinds of things like that. And so, but this is our defining equation for defining inductor equation, basically, whereas the ICDP is the defining cap equation. And if you're going back to basics, just like for the inductor, V equals IR, or for the resistor, V equals IR. These are their standard, their defining differential equations, okay? So this is where the Z equations and all those kinds of things come from, is these kind of foundational equations. All right, so let's say we want V sub L then. V sub L as a function of time is what we're talking about here. It's just L di dt. And so in this case, we want the voltage across all of them, so it's going to be L equivalent. And so we can just plug and chug. So it's just 35 millihenries times the derivative of 10 e to the negative 50 t amps dt, d by dt of that. All right, so 35 milli 10 to the negative 3, and then we've got the derivative of an exponential. You just, coefficient just comes through, and then the exponent, you multiply by it, and then e to the negative 50t comes back. And when we get this all carried through, it will be in volts. So V sub L of t is, whatever, it's got 10 times 35 e negative 3 times 50. And we got a negative in there, negative 17.5. X e to the negative 50 t volts. All right. So, oops. So we had the current was here. It starts out at, if we're plotting I of t, starts out at 10. It's a decaying exponential. Does something like this. The voltage is going to be starting out negative, and then it's going to approach 0 from below. V sub L of t. Physics writing is bad. All right, something along those lines. Of course, if we were given the voltage and had to find the current, we would have to do an integral, right? Going from one to another using the defining equation. Should we do one of those too? Let's just look at a brief example for a capacitor. So this could be number 4, I guess we'll call it. Number 4, if we have a capacitor, and let's say we know the current is, say the current is negative 10, just like we had for the inductor, but now let's say we know the capacitor current is 10 e to the negative 50t, and we want to know the voltage across the capacitor for that current. Right, so I is C dV dt, defining equation for capacitor. So what does that tell us about the voltage then? The voltage then, if we want to solve for the voltage, divide through by C, so 1 over C, the integral of I dt. All right, so if we want to get the voltage then for our capacitor, so V sub C, I guess, I sub C, all for the same element here. And so we've got to get V sub C then is 1 over C, the integral, was doing indefinite integral to start with, 10 e to the negative 50t dt, so 10 over C, and doing the antiderivative, you divide by the exponent of the exponential, and then you have your exponential back. So you use a negative 50t. And then plus some constant of integration we'll just put out there. All right, so to get the the total equation for v sub c as a function of time, we will need some sort of initial condition or something, but we have 1 over 5c, let's not call it c, let's call it k or something, because we already have c for capacitance, some constant of integration out there. All right, e to the negative 50t plus k. So say we were given some v sub c at 0. Let's just call it v naught for now. And so if we knew that, then we plug that in. We have 1 over 5c e to the negative 50 times 0, t0, plus k, right? And so e to the 0, anything to the 0 is just 1, right? And so we get v naught equals 1 over 5c plus k, and so k equals v naught minus 1 over 5c. That is weird. Let's see. Yeah, I guess when I did my example, I did v naught was 0. But anyway, in general, we can get k, we can get the starting value, or the value for k in our integration as v naught minus 1 over 5c, whatever that happens to be. Putting in numbers, it will look better. It's just some sort of a constant, right, depending on the initial voltage and on the size of the capacitor. And so our voltage then, well, yeah, let's start with the current. So the current, same as before, 10 tau decaying exponential with time. The voltage, though, what is the voltage doing? The voltage is some constant. Plugging this in, we get v naught, right? That's what happens with the, that's what we said. V at 0 is v naught, and then what does it do? So we've got a constant plus a decaying exponential. I feel like I have a sign problem here. Yes, I do have a sign problem here. We need a negative there. And so we have a negative here, a negative here, a plus there. Is that what happens? Yes. Yes. All right, so we start out at v naught, and then as the exponential gets bigger, as time gets bigger, the exponential shrinks. The exponential shrinks. Oh. What happens here? So k we're starting out at 0. At time t equals 0, we have v naught, and then as it grows, what do we get at time t equals infinity? At time t equals infinity, this goes to 0. And so all we have is v naught plus 1 over 5c. Whatever that is. So it's going to be a growing exponential that grows to v naught plus 1 over 5c. Very strange numbers. Okay. So this is the voltage across the capacitor. Okay, so the capacitor is going to charge up to that value unless I made a mistake. But I think that it's okay now. Putting in numbers will make it look a little bit better, but basically we're pushing current into it for a finite time, or for actually infinite, but pushing a bunch of current in. Eventually though, it's going to charge up. The current's going to go to 0 at infinite time, and the voltage is going to go to a fixed value after a long time, or at infinite time. Okay. I should work out examples before I start to do them on video, really. But anyway, let's go on to another problem here. Let's look at mutual inductance. What number are we on now? That was number 4, so let's look at number 5. So for mutual inductance, we have thinking of some sort of a core that has 2 or more coils wrapped around the same core. All right, so if we're causing a flux, causing magnetic field, causing a flux, the coils basically feel each other through the magnetic core. The same field is interacting with both coils, and so they have a mutual interaction, and so a current over here, for example, can cause a voltage over here. And vice versa, if we push a current through over here, or changing current anyway, it's all V is L I D T, right? It's all inductor kind of things, but it can cause then a voltage over on the V1 side. So we call it mutual inductance. The coils, one coil can get voltage from the other, right? A mutual effect because they're on a shared core of some sort. Okay, so we will have then, for example, V1 we'll have our normal L d I dt for its own current, and then we will have some, let's just put plus or minus, M di2 dt. All right, so it's going to get some voltage 1 has a component that comes from its own inductance, but then it has a component that comes from the mutual inductance. And so, and the mutual is plus or minus, is adding or subtracting depending on, when we put the currents the same way, like the way I've drawn this first current will try to make a flux this way, whereas and the second one is trying to make a flux this way, so they're actually building each other up, so they agree, so we would have positive. But if we rewound one of these the opposite direction, or took the current going the other way, basically if we rewound it the other direction, then they would have a negative effect on each other, and one making I1 be large could cancel out the field caused by I2. All right, or we could just think of turning I2 around. If we turned I2 around, for example, had the current coming out here, then we do the right-hand rule, then I2 is trying to make a flux or a field going up, and so they're fighting each other, canceling each other out. And so depending on how the coils are wound or how we're defining the currents as positive, we can get a plus or a minus in our M. And so the way we take care of this sign convention is by, when we draw a circuit, we'll have 2 coils, maybe different things in the circuit, maybe capacitor even, I don't know, just some sort of a circuit, maybe has a voltage source over here, maybe an AC source, something. All right, so if we've got L1, L2, but they're mutually coupled, we will do what we call a dot convention. We'll put dots on them and do a mutual inductance. So M is an inductance. It's a mutual inductance between the coils, and we keep track of how they're wound by where the dots are. All right, and so current into one dot, say this is I1, this is I2, current into one dot will cause a positive voltage at the other dot. So if I1 is going into this dot, it's going to make a positive mutual voltage on inductor 2, right? And vice versa, current going into the positive dot here will cause a positive voltage here, right? If current was going out of the dot, then it would make a negative voltage at the other dot. All right, hopefully that makes sense, maybe. And so let's just, so let's write the equations for these inductors. So let's define the voltages, normal, passive sign convention where current goes into the plus of the voltage, right? So we'd put current going into this side of the inductor, so that's the plus side. Current goes into this side of the inductor, so that's the plus side. All right, so if we want to write then V1 as a function of time is L di1 dt, and then what is going to happen, we're going to have, this is going to be plus or minus on the mutual, so we're going to put something m di2 dt. I2 is defined to go into the positive dot, and so it's going to make a positive at where V1 is positive, so they agree with each other. All right. If we want to write V2 as a function of time, we should put a 1 on this one because it's L1, yes. It's going to have its own, and we made it positive sign convention, so it's L2 di2 dt. Now, some plus or minus m di1 dt. And again, so if I1 is going into the dot, it's going to make a plus voltage on L2's dot, and so it's also plus. All right, so we got the nice positive sign convention. Everything positive, right, the way we defined it. But let's say we had a different circuit or same circuit drawn with currents defined different. Let's put the dots in different places. So let's do this. L1 and L2, V1 and V2. Everything the same, except we'll have this dot over here and the other dot on the other side. Okay, so now what's going to happen? So let's write the equations for V1, function of time. So again, we've got the current going into the plus for itself, so it's positive on itself. So V1 is L1 di1 dt. And then we're going to have plus or minus m di2 dt. But is it plus or is it minus? So looking at I2, it's going not into the dot, it's going out of the dot, right? And so current, so I2 is going to cause a negative voltage at the dot, negative voltage at I1's dot, right? So I2's current is going to do a voltage like this, minus plus from 2 I di2 dt, you can think of it that way. And so according to V1, that's the opposite of what is defined, right? And so we're going to have a minus sign here, right? Because the current is going out of the dot, or it's going into the opposite side of the dot, and that causes, anyway, basically flipping over the way we're doing the right-hand rule, and it causes to be a negative m di2 dt. Okay. Basically, anyway, you can look at the dots, and if they're opposite of, if the current's not going into the dot, we're going to have some negative signs, right? So let's look at V2 of t. Again, it's defined positive with respect to itself, so V di2 dt, L2 di2 dt is good. We're going to have some m di1 dt. But again, looking at V2, what is I1 doing? I1's going into the dot, all right? And so it makes a plus voltage at the dot, right? So it's going to make a plus voltage at this dot, plus, minus, right? This is the m di1 dt kind of voltage, right? Plus at the dot, because it's going in, current goes into the dot, makes a plus voltage at the other dot. but it's the opposite of what V2 is, right? V2 says plus is here. The MdID1, dt says no, plus is here, the opposite, so it's going to get a minus sign. All right, hopefully that makes sense. Should we try one more? Let's see what other examples I have here. Well, hopefully that's good enough. Hopefully that makes sense. If we were doing KVL, KCL, whatever, KVL with voltages probably, we could use these voltages then in our KVL equations. This whole thing, these two terms would be the voltage V1, and these two terms would be the voltage V2, and we could do the capacitor voltage, not set up very well, I is C dV dt, so V is integral of I dt, voltage here is IR. We could do KVL equations, do some solutions, things like that. And we can also do mutual inductance in frequency domain, which is where it makes the most sense, where we have phasors and so forth. And then we wouldn't have dIdTs, we would just have J omega L and J omega M, right? And then it would be I's, the I's and V's would be phasors. But mostly we just want you to understand the dot convention, how that affects the mutual, whether it's plus or minus. Okay, let's look at another kind of problem here. So switching gears a little bit again to look at AC circuits now, back to AC. And let's say we have a circuit here, it's kind of a bunch of stuff. This is a circuit we kind of did before maybe, or one similar. That was just resistors, but now let's go ahead and do it with a mix of, looks like maybe this was supposed to be an inductor. Mix of resistors, capacitors, and inductors. And let's see, this is a current source, and we're going to be in AC world, constant frequency AC world. So let's say this is a 2 amp phasor, and let's say this is 1 angle 10 degrees phasor, RMS phasor stuff. Let's say this is 250 millihenries, 200 ohms, 15 microfarads. All right. Let's define this as a ground node in case we need it. All right, and let's say we just want to find voltages. So let's name this voltage V1 and name this voltage V2. So we want to solve the circuit, find the voltages. Okay. It's set up as a node voltage kind of problem, so let's do it as a node voltage kind of problem. So what do we need to do first? Well, looking at this, we need to have the circuit, we can't have R's, L's, and C's mixed together, right? We need to have them all be ohms, right? So we need to figure out what is, we may need to make them Z's, right? Because this is an L, right? This is an inductance, this is a capacitance, this is a resistance, right? Or it could be an impedance. But we want them all to be Z's. So easy one first, Z of the resistor is just R, is just 200 ohms, right? Z for a capacitor, 1 over J omega C, or negative J over omega C. Just thinking about multiply top and bottom by J to get negative. So Z of the capacitor is negative J, and then, oh, don't do that. Okay, is just we need a frequency for our circuit. Are we going to just do 60 hertz? I can't remember. Yep, looks like I did 60 hertz. So we'll say omega is 2 pi 60, which is our 377 radians per second kind of number. All right, so this is negative J 1 over 377 times C 15 times 10 to the negative 6 farads radians per second. So Z for a capacitor is 1 divided by 377 times 50 negative 176.8, negative J 176.8 ohms for Z of our capacitor. And then we need Z, everything needs to be Z, so let's get Z of our inductor. Z for inductors is J omega L, J 377 times 250 times 10 to the negative 3 radians per second, henries. So Z for an inductor is J 377 times 0.25, 94.25, 94.25 ohms. Okay, so let's just write these in here, I guess. J 94.25 ohms, 200 ohms, and negative J 176.8 ohms. Getting a bit messy here. All right, so now we want to do node voltage method. Node voltage method says add up the current, do KCL at the nodes. Notice I didn't put a node voltage here. Why not? Because all of this is one node, right? All of this is one node, right? There's nothing separating this point from this point, no element separating it, it's just wire, so it's all one node. So this is all the ground node, right? So we just have these two nodes besides the only three nodes in the circuit, right? And so let's do KCL at node 1. What do we have? So we're here at node 1. So we have, usually when we're doing node voltage method, we like to add up the currents leaving the node, just because we can do V1 minus V2 kind of thing. So let's do the first one. So we want the current going through the inductor. It's going to be V1 minus V2 over, so remember we had, when we were doing it with resistors, we had V equals IR, so I was V over R. Now we have, in complex, we have V equals IZ, so I equals V over Z, right? And so V over Z for this one, V plus here minus there, so same like we did for resistors, but now we got to divide by not L, divided by the Z, so divided by J 94.25. So yes, everything is complex numbers, all math is complex now, okay? And then leaving, we've got this current source here, but it's actually entering, so it's going to be minus 1 at angle 10 degrees. And then this one is leaving, so it's going to be plus 2 at an angle 0 degrees, 0 degrees. And those are the three branches touching that node, so that equals 0. Right, so all the currents leaving, the sum of the currents leaving equals 0. And so, well, let's write the next equation and see what we need to do about solving things. So KCL at node 2, right here. So we can go ahead and do the inductor first, but now we're going to want the current going this way, so we're going to have V2 first, this side positive, that side negative, so it's going to be V2 minus V1 over J 94.25. Right, I is V over Z. And then for this branch, we want the current going down. The voltage is V2 minus 0, so it's just V2 over the Z of that branch is just the resistance, 200 ohms. These are all ohms, all of these are ohms. Okay, so that's that branch. And then we got this third one here, plus, what's the voltage here? It's V2 minus the voltage here, which is ground. So it's just going to be V2 again, V2 minus 0, over Z of the capacitor, which is negative J 176.8 ohms. And those are the three branches touching node 2, so that's all we got, equals 0. Alrighty, so now we have two equations, two unknowns, so we can solve. It's complex, so we have, it's kind of like we have 4 variables because each complex number has 2 parts, but we can do the math complex wise. So let's make a matrix. Let's write them in a nice form to make a matrix out of them. So we're going to have 1 over J 94.25 times V1, starting on this equation, and plus negative 1 over J94.25 V2. Let's bring those other things to the other side. So then we're going to have 1 at an angle of 10 minus 2 at an angle of 0. Alright, and so let's just combine that while we're here. So 1 at an angle of 10, now my calculator, we do, if I can remember the book, shift of the book, get the angle sign, there we go. 1 at an angle of 10 minus, and 2 at an angle of 0 is like 2, it's just a real number. Angle of 0 means it's purely on the real axis, so it's just 2, so minus 2, okay? 2 at angle 0 is the same as 2, so, okay, doesn't like that. We need to put this in parentheses. Hopefully then it likes it. Yes. And so this equals, yeah, negative 1.015 plus J.1736. Okay, complex number. Those two combined. All right, that's node 1 equation. So node 2 equation to get in matrix form. What's multiplying V1? Just this same thing, except for negative 1 over J94.25 V1 plus, gonna have a couple things multiplying, or 3 things multiplying V2. And that one's gonna be equal 0. I like that. So V2, we've got 1 over J94.25. We got a plus 1 over 200. We got a plus 1 over negative J176.8. You still see? Yes. Good. Okay. So we're running out of room. To put this in matrix form, you know, calculators, MATLAB, computers can do complex math in matrix form, just the same. And so we're going to have our solution. We're going to say V1 over, no, our vector V1, V2 as a vector equals, we're going to take the coefficients to make, and then do the inverse of that and multiply that by this B matrix, right? And get the answer. So to plug in, we're going to have 1 over J9, not negative, 1 over J 94.25, and then negative 1 over J 94.25, negative 1 over J 94.25. Hopefully you're getting the idea here. And then this whole thing in there. Ugh. 1 over J 94.25 plus 1 over 200 plus 1 over negative 176.8J. And then this becomes the vector here, 1.015 plus J.1736 and 0. Yuck, what a mess, but calculator wise, you can do it. So let's get a matrix. Let's see, 7, 1, 1. We want a 2 by 2. And so the first one is 1 divided by, let's put it in parentheses so we don't lose I, times 94.25. Wish I knew how to copy. It would be nice, but anyway, let's do it again. Negative 1 divided by, in parentheses, I times 94.25. Yes. Same thing there. Negative 1 divided by I 94.25. 25. And over here, a bunch of stuff. 1 divided by plus 1 divided by 200 plus 1 divided by negative I times 176.8. Okay, getting to be a mess here. Get out of the matrix, do my little inverse to the power of -1. And then get down and get a vector. 7, 1, 1. Number of rows 2. Number of columns 1. Alrighty. And on the top we have -1.015 plus I times 0.1736. And at the bottom we have 0. Alright, so I got this, I think, whole thing entered into my calculator. Okay, and so it gives me this thing which does not look good. I should have checked my work here. Alright, what went wrong? Got the 1 over J, 1 over ZL, negative 1 over ZL, negative 1 over ZL. Alright, that does not look like a 1 over ZL there. Let's get that back and fix that. Let's see, can we put that in parentheses? And then 1 divided by that. Okay, so we got 1 over ZL, 1 over ZL, 1 over ZL, 1 over R, 1 over the capacitor. That looks more like something not what I had before. Let's just double check. -1.05 -1. Shoot. No, negative. Oh yeah, -1.05 plus J times 1.3.137. Yep. Okay. Maybe it's okay. So let's see. So we've got negative 16.4 minus 95.7 J and negative 4.21. Nope. That one's little. Negative 0.00421. Doesn't look good. Plus 0.0058990 plus J. Alright, well, let's see what we get. And so usually we like to have our voltages, voltage and current phasors as in polar form. And so let's go ahead and see what we get there. So 16.4, negative 16.4 minus J 95.7. And then we're going to remember how to get to polar, so I think we need number complex is 9, convert to polar is 6, enter. Alright, so it says V1 is 97 at an angle of negative 99.7 degrees, and says V2 negative 0.00421 plus 0.00590 times I, put that in parentheses, go to number, complex, polar, enter. 0.00725, angle of 126 degrees. Volts. So kind of strange numbers where the voltages are very different from each other, which is not what I had when I did the example problem the first time, unless I read my calculator wrong. But I don't see the errors, so we'll go with it. Hopefully the method, hopefully can see the method there and the final result. But I guess the punchline is, once we get everything in an AC circuit like this, we get everything converted to impedances. All the R's, L's, and C's, we make them all into Z's according to their own formulas. Then we just treat it like a resistor circuit. We can do Ohm's law, we can do KVL, KCL, no voltages, meshed currents, Thevenin, Norton, all those kinds of things. We can do the AC version, which is very similar to the resistor and DC version, but all the numbers are complex, so the math is a bit messier, and very nice to have a calculator that can handle complex numbers and do polar to rectangular conversions, not to mention matrix math. For the test and for things where you're time limited, I'll try to have you just mostly set up the equations and not waste a bunch of your time trying to do a lot of algebra. I will expect you to be able to do the basic polar to rectangular conversions and understand how those kind of things work, like we've done like we did in the previous homework. But yeah, you aren't required to have a super duper calculator that can do all of this easily, so we'll try to level it out that way. Okay, I think we'll stop with that example.